Okay, 10 seconds are passed, seemingly. Okay, hello everyone. Okay, back to the teaching. So, you had the course with Fabio Romanelli, that was a course on seismology. This was theoretical seismology, and anything that you've learned with Fabio is connected to the way we look at earthquake using seismic waves. Okay? And then what we will be looking here in this course module is a little bit complementary. It is different, but it relies a lot on what you've learned in the course on theoretical seismology. So this is a sort of maybe my favorite description of what an earthquake is, okay? Maybe you've seen it in the first semester, but you will see it again in the second semester. We'll get in details into some different aspects. So an earthquake is a term used to describe both sudden slip on a fault and the resulting ground shaking and radiated energy caused by the slip. Okay? So the wording here is very important. The first wording that you see here is sudden slip. Then we're talking about slip. Then this course would be teaching you basically how to look at earthquakes but viewed from a slip distribution rather than from the ground shaking. Okay, rather than from seismic waves. Then when you see this wording, you do not see slip alone, but you see sudden slip. Then it gives in some ways a timing to your slip. Okay, then the word sudden includes a certain timing. Okay, then you can understand that this should be very short. Okay, and the second important wording is the fault. Okay. Then what does this mean? Getting you back to the theoretical seismology course, we will not be working within the point source approximation, but we will be getting into the extended source approximation. So anything that you will hear during this course module will be observing an earthquake not as a point, but as an extended source. Okay? Then things will become a little bit more complex. And this is the most realistic way of looking at earthquakes, of course. But this does not mean that the point source approximation is wrong. You know the limits, okay? You know the plus and you know the minus, okay? So, and then the other wordings that you see here, if we have time, we will get into energy issues, okay? And the energy will get us a little bit more into not the kinematics of faulting, but we will get into the dynamics of faulting. Okay, then what you did up to now with Fabio is mainly looking at kinematics. But you will see the kinematics on my side, but not from a point source approximation, not just from a single focal mechanism, that you did the course on focal mechanism, what focal mechanism is, but you will see the source in its complexities. Over an extended fault, and the source will become extremely complex, you will see that the geological fault, it can be complex in the field when geologists go and map that fault, but when it gets reactivated by an earthquake, it can be even more complex than what the geologist could map out. Okay? And we will see the reasons behind. Okay? Then the take-home point here is that you have the wording slip. Okay? Now this will be our measure of the size of an earthquake. And there will be the term fault that will be also a measure of the size of an earthquake. Bigger is the fault, the larger will be the magnitude of the fault. But you will see that I can generate even a large earthquake with a relatively small fault if my earthquake is complex. Okay? And then in the first semester, we've been also defining what a down dip extent is and how the down dip extent is important in the maximum magnitude estimate. Okay? Then we won't be talking about seismic waves, but my assumption here is that you guys have been basically, you digested now the theoretical seismology course, then you know everything about seismology from the theoretical viewpoint, from the seismic wave viewpoint, and now we'll get into a little bit of more mechanics. Okay, let me start with the end. So if you know this, you do not need to follow my course. Okay, so this is the end of the course. The end of the course means that if we are able to understand that a plate boundary, okay, is made of a number of faults and how these faults are accommodating the deformation that is induced by plate tectonics, then you do not need this course. And if you take one single fault here within your system, and you know how this fault is moving, one single fault could generate a wide spectrum of deformation. And recalling the first semester, what we've learned is that we need to think always in time and space. Time and space, right? These are time-dependent processes that are taking place on one single fault. It means that one single earthquake fault could generate all the spectrum of deformation. Okay? Then one single fault could generate a normal fast earthquake. Okay? Like the San Andreas, it generates earthquake. At the same time, this fault may exhibit all these types of behaviors. We will understand all these behaviors during the class. Okay? Then it goes from what we call a seismic slip. It's a slip without a release of seismic energy. Then you do not get a ground shaking, but there is a time-dependent slip going on, but it's a seismic slip. It's without releasing of an elastic energy, but it's accommodating deformation though. Okay? You get into what we call creep events. This is like a seismic slip, but the word creeping is mainly used for the shallow part of the fault. I'm getting into the space domain. Okay? Then I'm making my shallow part of the fault slipping seismically. We have what we call a strain transient. Here we're talking about strains. It means that it could be, we'll be learning a little bit more about strains, okay? It could be something that we still do not understand whether this is a slip of the fault. It could be a volumetric deformation within the system, but we do not know the way it takes place over the fault, whether it's accommodated by the fault, or it's a poroelastic rebound within the system, or it will get complicated, right? And then we could get what we call a slow earthquake. It's like it gets into the time scale of an earthquake. Time scale of an earthquake are seconds to minutes for mega earthquakes, okay, in terms of rupture propagation. But it's far slower than it may require maybe 1 hour. But it's like an earthquake. You could get the long periods within your wave train, but maybe you'll miss the high frequencies, right? You could get to episodic tremor. It gets into really complicated stuff that we see in subduction zones. We will be understanding these processes. We'll get into silent earthquakes. These are forms of slow earthquakes that maybe do not even release any type of waves. And we get to transients and after slips and post-seismic deformation, slow precursors to normal earthquakes, earthquake with a distinct nucleation phase, and then till you get the normal fast earthquake, and then you get an earthquake with a supersonic rupture velocity. Then, question for you guys that did this theoretical seismology course, what is a normal earthquake? Okay, this is for Donna because she does not know me. The way I teach is extremely interactive, whether we are on YouTube or no. So this is first a class for the students, but I mean, I expect the students to be part of it. Okay, then what would be a normal earthquake within this spectrum? And then I'm calling this as a sort of a fast earthquake, but it's not a supersonic earthquake. It's not a super shear earthquake. Then what would be a normal earthquake? You're supposed to do the exam in seismology. When is this? Soon? Okay. What is a normal earthquake?
The shaking.
Eh?
The shaking of the surface of the earth?
No.
Where it results like in a sudden release of energy from the lithosphere that creates seismic waves?
No. It is a very, very technical answer. Yes. When the rupture velocity is 80% the velocity of the media. This is what we call 80, 70, whatsoever, 85, but it's less than 90%, less than 100%. Then this is what we call a normal earthquake.
Oh.
It's when the rupture velocity of that earthquake is 80% of the shear wave velocity of the media in which the earthquake is traveling. Then what would be a super shear earthquake? When the rupture velocity exceeds the velocity of the media, the shear wave velocity of the media, right? So then a question for you guys is, what is the Vs of the crust? What is the shear wave velocity, the average shear wave velocity that you would expect in the crust? You need to have these values on the back of your mind.
4 kilometers.
That's 4 kilometers per second for the crust. This is too high. So you're almost getting into the mantle. And it's less than 3. 3 something. In the upper crust, it's 3 kilometers per second. Okay? Then if you have an earthquake that has less than 3 kilometers per second in between 2 and 3, then this should be a sort of a normal earthquake. Right? Okay? This is extremely important. Then this slide is basically showing us how complex can be one single fault. Okay, the wide spectrum of deformations that we would expect from one single fault, which are plenty, okay, and then we will see what is the physics that stand behind this wide spectrum. And then now, in this model, what we're trying to understand, that we're making a little bit our life more complicated, okay, is that we're getting one single fault into the plate boundary, but it's not just one fault, but it's a system of parallel faults. And I'm just getting you into a less complex plate boundary. So the simplest plate boundary would be one single fault, right? Then you have one single fault on two plates that are, you know, slipping one past the other one, right? Then if I have a complex plate boundary, then I can put another parallel fault. If I would like a more complex, then I put a number of parallel faults. But if I want it extremely complicated, then I can have even perpendicular faults or oblique faults, and then very complicated faults. Or one single fault could be even more complex, not just a single line. Okay? And we'll get into these complexities. And then this slide is basically hinting to two different things. Okay? We're getting into from a model by which what we're trying to understand here, that in this first part we're trying to understand how a single fault is moving in time and space, and we should be able now to understand all these processes, because we're not putting these processes on the blackboard because we do not know them, but we know these processes now, thanks to GPS, thanks to seismology, thanks to INSAR, thanks to classical geodesy, okay? They've learned space geodesy a little bit, okay? Then we're getting from one single fault, and here the idea is to understand how the big picture, which is plate tectonics, or deformation within the continent, is transferred, is accommodated by each single fault, right? Okay? Now, here it's one single fault, it's one single object, very simple, and we see that one single object within the system can exhibit different time and space deformations with different velocities of rupture. But here we're talking about velocity of rupture because you guys learned this from the seismology theoretical course, but here we will be later on talking about seismic slip velocities, which are two different, completely different things, okay? Why the rupture velocity in seismology is quantified with kilometers per second, and the seismic slip velocity on a fault is quantified with what is the difference between a seismic slip velocity during an earthquake and the rupture velocity? Tom?
Rupture is a kilometer per second.
Right, and the seismic slip velocity is?
Is a centimeter per second. I
That's great. Yes, this is meters, centimeters per second. Okay. This is really the displacement that you have on the fault, right? Okay. When we talk about rupture velocity, we're talking about the rupture front that we get from the seismic waves. Then the second object now is taking us out of this one single fault scheme, but we're getting into a scheme by which we would like to understand how plate tectonics, okay, the big picture, how the strain that is coming from plate tectonics is accommodated by single faults. Okay? And then we know from this picture that this strain could be released in some ways by these different processes, right? So then plate tectonics, a plate is your lithosphere that is basically sitting above your asthenosphere, and it's two lithospheres that are colliding, or two lithospheres that are getting one far away the other one, or two lithospheres that are moving one aside the other one, right? And now the strain that you get from plate tectonics, that you get from mantle convection, okay, how does this strain get distributed on faults? Did you ever ask yourself the question? So these are the questions that you need to answer. Okay, and these are really extreme models. These are end-member models on how the plates are transferring their energies or their strains to single faults. You start from the first model is called a distributed model, by which your faults stop basically at the intersection between your schizosphere and your blastosphere. What is the difference between schizosphere and blastosphere? Yes, sir?
Schizosphere is a brittle part of
That's the brittle part. It's the part that deforms elastically. And the blastosphere should be the flowing part, right? So then, in case your fault shuts down here, then this is what we call a distributed model. In case your fault, this is the other extreme model, in case your fault go down and sample by themselves the blastosphere, where you have the flow, right? So then we need to understand whether we are in this system or in this system. How can we do this? Well, I alluded to this in the first semester. Yes?
I calculated the depth of earthquakes.
Well, if you calculate the depth of the earthquake, you might end up, because earthquakes are basically taking place on the brittle part. But this is not telling you whether earthquakes are getting down within the flowing part. Because your hypocenter or your nucleation point will be always within the brittle part, right?
Yes.
Then your answer is not fully correct to some extent. So then what is the way out? To understand whether these faults are sampling the blastosphere.
Magnitude of earthquakes. The magnitude of earthquake.
No.
Yes.
No, the magnitude of the earthquake scales with the size of the fault that is still within the schizosphere. We're on again. Donna, you did not do the GPS. You would use GPS.
But GPS are used for to study the deformation. It's a crust as a surface, not deep down.
Well, then you need to use mathematics and physics to invert the displacement field that you have at the surface down to a certain depth. To understand whether the fault is sampling the blastosphere, then I will rely more on time-dependent deformation. They are a little bit out of the scope of classical seismology. But still, classical seismology will definitely tell us whether the faults stop at a certain transition. And then we've seen this in the first semester, that the classical depth, 15 kilometers, 10 kilometers, may hold in some places, but it may not hold in other places. We have places within the continents where the seismicity goes up to the base of the crust. So we have earthquakes within the lava crust. Okay? While understanding whether our faults are cutting down within the blastosphere, I really need to rely on other tools like GPS. And we will discover this step by step during this course, and how to use GPS to understand whether the fault is sampling down within the blastosphere or not. Okay? So these are extremely important models. If you do then understand the way the deformation is accommodated by single faults within your plate boundaries, and you understand the way each single fault is behaving in time and space, then you know everything. You know everything. You know almost everything. So you're doing very good. So this is extremely good. So there are few places in the world where we know all this type of behavior. So these are PhD physicists. I mean, students spend time and then they focus on a region and then try to understand how the deformation is accommodated on single faults from the plates, from the regional geodynamics, and how a single fault is behaving. Okay? So this is the end. Now the title of this part is that we've come a long way in monitoring and modeling earthquake deformation. This is, when I started doing my PhD myself, we were unable to talk about all these processes. So things have been changing incredibly fast. And all this because of the advent of GPS. Okay? GPS has been allowing us to understand all the time-dependent processes. GPS and INSAR depends. Of course, the resolving power is different. These two instruments do have different resolving powers. And then you heard some of the resolving powers during the course of Alessandra for GPS. But we'll talk a little bit more about INSAR as well in this course. So then, the first thing that you need always to remember is that an earthquake is taking its slip on a fault, and this fault is embedded within a media, right? Then the fault in this course will be complex, and the media will become even complex. Okay? In seismology, you observe the elastic part, okay, or at least from the release of earthquakes using seismic waves. Okay? While if you would like to understand the rheological profile of the Earth, you really need to get to GPS. You need to get to space geodesy or classical geology, or any means that allow you to chase the time dependency. So, and here, if we would like to understand earthquake mechanics, then we definitely need to understand also the fault mechanics. So the mechanics of earthquakes and the mechanics of faults are two different entities that are connected, of course, because an earthquake is taking place over a fault. But a fault has its own mechanics. A fault is a geological object, right? A fault is there since, it could be since millions of years, or it could be since thousands of years, okay? And then an earthquake has its own mechanics because it's a process that happens over seconds and minutes, right? And further to this, we have the mechanics of the medium. Okay? Then in this course, we will learn about mechanics of earthquakes, mechanics of faults, and mechanics of the lithosphere. Okay? So, then we have an earthquake that is taking place on a fault, and the fault is embedded within the medium. And then in a few minutes, we will discover what is the best analog to understand this from a physics viewpoint. Okay? So if we would like to get to these processes, if we would like to understand the mechanics of a fault, we can't just look at the mechanics of an earthquake. Then we need to look at the way earthquakes repeat over time within that, on the fault itself. And here we're talking about the earthquake cycle, right? And the earthquake cycle is made of, this was the very simple first model of deformation that we came out following the Reed model, San Francisco. I think that Fabio has shown it already to you. This is a stress loading or a strain loading on a fault. Okay, then I'm loading the system here, and this is timing. Okay? And then at some point, my stress loading, or the external forces within the system, will be far higher than the frictional forces on my fault, and I'll get the earthquake, right? And then this repeats over time, and it goes on. Okay? This is a very simple model, and then this model, it looks like a periodic one. Okay? It's the same timing. This is completely wrong. We know that this does not work much. There are faults that might exhibit some periodicity, but this will be open for discussion, but this is not something that you need to think about now, but we will talk about these issues during the specific topics. Okay? And this is without any transient deformation within the system. This is a very simple model by which you take a fault that is locked, okay, and it gets strained over time, and then the strain at some point builds up till the frictional resistance on the two planes are not able to withstand the elastic restoring forces, and then you get the earthquake. Very simple model. But what we know from rock mechanics experiments, that this is not the case. If you take a very simple material, this is coming from Frost and Ashby in 1982, this is a creep cycle for constant loading. Now this is the same constant loading, and the constant loading is coming from plate tectonics. Let's think this way. Okay, plate tectonics might be a constant process over certain thousands of years. Okay, could be quite constant, but it might change in time as well, in geological time scales. And then you have one sample here, and then if you take this sample and then you squeeze it, either in 1D or 2D or 3D, or you do a triaxial, this is with different, you stress your material not only through a uniaxial, it's not a uniaxial experiment, but it's a triaxial experiment. You get first, your sample will start exhibiting, this is strain versus time, a very transient primary creep. And then it gets to a steady secondary creep, and then it accelerates before the rupture. This is what you learn from rock mechanics, okay? And these are the initial models that we got after the plate tectonic revolution started coming out, okay? So this is telling us that this is very simple, okay? Then there might be transient within the system. Then anything that is transient is a nonlinear behavior within the system by which your strain behaves over time. And your strain is not exhibiting anymore a steady state, but it's nonlinear, right? Very, very simple stuff. Extremely basic. So seemingly, now I will show you the state of the art now. So this is our thinking many, many years ago when we started understanding about plate tectonics. Plate tectonics goes back to the 60s, right? But the Reed model of, strain accumulation started after the 1906 earthquake. But we didn't have plate tectonics in which to insert our strain loading process, right? And this is what we all were understanding in the 60s or in the 70s of what an earthquake cycle may look like. And this is stress or strain over time, right? This is the actual earthquake cycle. It gets complicated, okay? So this is plenty of work, plenty of physics, plenty of papers published, plenty of data sets, plenty of new technology, and this is the state of the art up to 2010. This is a paper in 2012. Okay? We start to know a little bit more, but a little bit less, but still, it does not look like this system at all. A very classical loading process, and then a release of energy with slip on a fault, and load up, and so on and so forth. So during this course, we will get into these processes, okay? And we will look at the earthquake cycle, but not from just a very simple steady state stress loading, and then a release, and then a loading, and then a release. This is respectable, of course, but we will get into complicated schemes. And what you see here, I'm putting now my timing, and then you see that the earthquakes are not periodic. We have times between earthquakes that are larger, and then here smaller than this, and then it could become a little bit like the first one, and then shorter, and then bigger, and so on and so forth. Then the recurrence of earthquakes becomes non-periodic. Okay? This is the first order observation over the time. And the second order observation is that my shear stress, or my whatsoever you're looking at, is behaving completely in a very different way than the classical one. So if we look at the slip, then you see, for instance, anything that is slip is what is represented in green. Then what you have is that slip starts likely to increase before the rupture. Then you have a sort of a nonlinear behavior here, and then you get your rupture, and then afterwards you have your slip is behaving right after the earthquake in a nonlinear fashion till it gets to a flat, and then again. So you see that the slip distribution is completely different. Here you get a mega earthquake, a very large one, larger than this, okay? So then the co-seismic slip is this value. You have a pre-seismic accelerating creep that might be shown, that might be exhibited. These are good news if you would like to predict an earthquake, but it might be bad news because it's difficult to chase these values, these entities. And there are still faults that are not exhibiting these pre-acceleration creeping. Okay? Well, we've seen, I mean, we published even papers here on Italian earthquakes where we've seen a sort of a slow slip before an earthquake. But we can't tell what would happen after that creeping, whether I get a release of a large earthquake or the system would get back to its normal behavior. So earthquake prediction for now, it's out of the reach. But physics of earthquake prediction is an interesting field. Okay, it's research, but it won't be these time scales. We will never be able to predict an earthquake within the short time. Okay, you'll never be able to tell to your president in Ethiopia, hey, tomorrow morning I'll get an earthquake in Addis Ababa. Just forget about it. Okay? So looking at the slip is telling us, this model is telling us that the slip distribution within the earthquake cycle is a complicated object. So there are transient, there are steady state behaviors. And if you look at the shear stress, likewise, I mean, the shear stress is behaving in a very, very complicated fashion. If you look at the fault strength, okay, which keeps your two faces of your fault locked, okay, and the fault strength behaves also with a very complicated object, by which you have what we call a healing process. A healing process means that after the earthquake, your fault starts to heal up. You know healing? You know what healing means? You know recovering, when you cut yourself, and then you get the blood coming out, and then that place will start healing up. That's exactly what happens on faults. Faults do heal up. And when they heal up, they exhibit a certain type of deformation. Is a change within the distributions of stresses as well. Okay? Then you see that the earthquake cycle now is viewed in a very, very complicated fashion. And in this slide, basically, we're putting plenty of different information. This is seismology, space geology, modeling, and rock mechanics experiments. But who can tell me what is the magic parameter that controls all this behavior? The first order parameter that control on faults, that controls this behavior. Why we have these different types of behaviors on a fault? On a fault that is able to transfer large earthquakes in time with different sizes. What is the name of this magic parameter? You're living in a room here that is called Leonardo da Vinci. Leonardo da Vinci got it many years ago. You know, Leonardo was a big fan of dancing. I don't know whether I've shown you the slide in the first semester. You've seen it? No? And he was talking about friction. Friction is the parameter. And he said that, and the dancer will cease. You know, it's like when you dance, you slide over the floor, and you slide over the floor thanks to the friction, right? And you control your sliding. If you do tango, you're a big fan of tango, so then friction is controlling this. Then we will have a specific course on friction. Okay, then friction is the mother of all problems here. Okay? And an earthquake is a frictional instability. So, then if we would like to look, so we've been basically, the way we constrain that earthquake cycle model is that if you would like to work at those time scales, you need different sorts of data sets within the system. You will see that seismology, what you've learned in your theoretical seismology course is, you know, one a very small snapshot of the whole picture. The seismic waves are telling you how an earthquake is going. Okay? And then you could use seismic waves to investigate the earth interior, which is another issue that we will be talking about. But if you would like to understand the way a fault moves in time, you need to make use of different types of data sets. What I'm plotting here is basically time versus, this is time versus strain. Okay, this is strain. Okay, then I'm getting to larger strains, smaller strains within the system. You know, small times in terms of years to million, right? What we call a stable continental region, it's a region that exhibits small strains, and earthquakes may occur with large time intervals. Means that if I have a fault here in a stable continental region, a stable continental region could be Canada, for instance, could be some specific places inside the plate belt, not far away from the plate boundaries, okay? But you have faults there. And these faults may generate earthquakes. But the way in general earthquakes repeat on these faults require longer time span for the accumulation of strengths on these faults. And here we go into plate boundaries. These are really fast regions that are straining fast, and the recurrence intervals on faults are within the reach of 100 years. I mean, there are faults that could be reactivated in a 100-year time span. Look at the California, you look at big subduction regions, look at the Himalayas, okay? And then you have in between active plate interiors. And if you would like to study a fault, if your president is giving you funding, and then he would like to set a nuclear power plant within a stable continental region, you won't be able to talk about earthquake hazard if you do not use geological data sets. Because seismology, historical seismicity, what humans tend to remember, I mean, the grandmom of your grandmom of your grand whatsoever, if she was a historian, maybe she would report of an earthquake in Ethiopia. Hey, this is just 100 years after whatsoever. Okay, we got a large earthquake, and then, you know, this would remain in history. But if you're working in a stable continental region, you may see a fault in action only after 10,000 years. And history does not work. You need to move to geology, right? And if you have to design a nuclear power plant in a stable continental region, it becomes extremely complicated. Because it's not easy, because you need to take care of array of effects. You may have a fault nearby your nuclear power plant that has been loading since 10,000 years, and is maybe ready to go. And you need to use geological data sets to understand how active is the system. While when you get into plate boundaries, seismology becomes important, historical seismicity becomes important, but you need still to expand your time with geological data sets. Okay? Then a waveform, it's a seismological record. Okay, this is what we call a record of an earthquake. The seismic wave is a simple record of an earthquake, because we have a seismic wave, and this is the record of an earthquake. Okay? Geology, what would be the record from earthquakes in geology? It's a displacement on a fault. That you're able to go to the field and measure it. Right? At that time, in geological time, they didn't have instruments, right? So, no way. Then you need to integrate all these tools together in time and space to have a control of the earthquake cycle. Because we've seen that the earthquake cycle is not a periodic, is not as periodic as we have thought. If you take one single fault, it may look like a periodic system. But it's difficult to have one fault within the system. Even though you have one fault, you will not get periodicity, and you will see it in the analog system that I will be showing to you later on. Okay? And here I'm getting you into, if you pretend to do a thesis work on the earthquake cycle, and then you say, hey, I'm working not only on dynamics of earthquakes, but I'm working on fault mechanics, then you have to use geological data sets. You can plug them into your model, that's fine, but you need those type of data to expand. But this does not mean that you need to be a geologist. Okay, you need to work with a geologist, or you need to collaborate with someone that is able to give you reliable data sets and then put them into your model, right? To expand your timing. So this is another way of putting the things into a little bit of more detailed scheme than what we're basically doing here. We're putting the timing, and then we're putting the different fields. So while the first one was very specific to different regions in the world, okay, this one was specific to what we call a plate boundary, okay, and this is an active plate interior, and this is a stable continent. Now, I'm looking at the earthquake cycle in a little bit different way, but it's always the same way, because my plot is accounting for strain and time. Okay? This is the timing. I'm getting to 1 million here. And here, I'm looking at different fields that are required. Right? Let's look at it. And this is the earthquake recurrence, right? And if I'm in a plate boundary region, I may be within a 100-year recurrence interval. In plate boundary region, what is the rate of deformation within a plate boundary? It could be millimeters per year, it could be centimeters per year. It could be less than a millimeter per year as well. Okay? Then if we're in 1 centimeter per year, in 100 years, we get 100 centimeters. Then we have 1 meter. 1 meter as a displacement would be a magnitude 6, or 6 plus. If you have an area like San Andreas or Nepal, where we have more than 1 centimeter per year, then you get larger earthquakes. You can get even mega earthquakes, right? So, what do we use here? Then for the short time span, we can rely a lot on, classical seismology. This is seismology, this is space geodesy, and this is traditional geodesy. Space geodesy is GPS and NSAR that you learn. And we'll get again this on the table, we'll put it again on the table, and then try to understand a little bit better what you've learned with Alessandra. And then seismology, here, by putting seismology up to 100 years, okay, and geodesy goes up to this, and it could go even a little bit back forward as well in timing, but it means that I'm including even historical seismicity. Okay, then seismology starts from 0, and it goes up to here. It includes historical seismicity. It could go even, the largest earthquake catalog in the world is in China and Italy. There are reasons for this, right? History. Okay? Italians have a long history, but even Ethiopians have a long history. But maybe the history in Italy has been more well preserved than the Ethiopian history. Okay? And this does not mean that Italians are older. No. It's just a way that, In some specific places, it has been more well preserved. History has been more well preserved. So this has allowed the historians to build a larger earthquake catalog, where people were reporting about damages 1,000 years ago, 2,000 years ago. They were talking about, hey, there was something that was happening. We had the land coming down from the mountain in a very short time. They wouldn't talk about seconds and minutes because they didn't have this. Okay, I would say in a time where you cannot even drink water. Okay, then they put it in a frame by which you can understand. Then historians are extremely good in making use of those information and then saying, hey, this should be an earthquake. Okay? And this is what we call historical seismology that is not appearing here. And what we call paleoseismology, it's seismology within the paleo, okay? Then it goes within a time between history and geology. It could be even with archaeological times as well. Okay, this is what we call archaeoseismology as well. Archaeoseismology, it's a seismology that you could retrieve from archaeological sites. And then paleoseismology excludes the humans. Okay, and there we need to go and date the material that has been displaced. Okay, and then we could use nuclear physics to date, right? C14, for instance. And then you get into what we call tectonic geomorphology. And then tectonic geomorphology has in some ways what we call short wavelength and long wavelength topography. Then tectonic geomorphology, this is the geomorphology on a single fault. Then if you have displacement on one fault over time, over thousands and thousands of years, you see that that fault will control the landscape. It will control the topography, right? The same thing, this is what we call a short wavelength. It's a wavelength on the fault, right? And then you have a longer wavelength, a bigger one, that could be at the scale of the mountain ranges, right? At the scale of the Piedmont of the Himalayas, or at the scale of the Piedmont of the Alps, or the whole Alps. But when you get into that big scale, then you might be including very deep processes in the Earth. Because bigger is your wavelength at which you're looking at the Earth, at the morphology of the surface of the Earth, then deeper are the processes that you're sampling, right? And shallower is the wavelength. If you see a gradient within your topography within a wavelength of 10, 15 kilometers, then maybe the source of that anomaly that you see in the topography may be sitting within a depth 1 or 2 times the wavelength. 20, 30 kilometers, or even less. Okay? So this is the concept of short wavelength or long wavelength topography. And then you get into the plate motion. You know, plates have been moving since ages, and now we have means to understand how the way plates are moving, and here you need to rely on a different expertise. Till you get to structural geology. Then structural geology, while in topography you see, for instance, as a mountain range, this is what you see at the topography, okay? And these are your trees. The structural geology should be the geology that would be telling you what is the geology beneath this topography. Is this a geology that fits the topography? If I have to put a geology that fits the topography, what could be the geology that fits the topography here? What could be the geometry of the layers that would fit this topography? It should be a geology of this sort. If these are your limestones and your sandstones and then your clays or whatsoever, then this should be a fold. Okay? Then a fold would basically generate this topographic scheme. Okay? And this is exactly what we mean by structural geology. While you could have a topography that is not reflected within the geology, by which your layers are completely different, okay, than the topography. And you need to understand the reasons. Okay? And you see that the timing gets a little bit different if you have to assess then if you would like then to have the larger picture, you need to put different data and integrate all these data in time and space. Okay? So this is a very simple picture that puts all these time scales into perspective. The first one is this one. This is the plate motion scale. This is your North America versus the Pacific. This is a huge scale. This is the plate tectonics. And here in the middle you have the San Andreas. These like a knife cut. Okay? You see it. It controls the landscape. Now this plate is moving against this plate with a velocity of 56 millimeters per year. This is 3.6 centimeters per year. And then this is 3.6 meters on 100 year. But this 3.6 meter is not taking place on the fault, it's taking beneath the fault, and then it's transferred to the fault. And the fault is stuck, and then it releases this energy during the earthquakes. And then if we zoom on a very small and tiny, here you see a big river that is caught. This is a cumulative, basically a cumulative displacement of several earthquakes on the fault. And then if we zoom on something of this sort, you would see this. This is your river, and then it gets, basically, its path gets disrupted by the fault, and then at some point it ends up in the fault, and then it follows the fault till it crosses again. So this is an offset. This displacement would be a cumulative displacement that is generated by 2-3 earthquakes in the past. Here we see a big plate motion. There are a number of earthquakes that are accumulating over time and space. Then we get into 36 millimeters per year. Till I'm showing you here the 1906 earthquake. And here you do not see two rivers that are displaced with a cumulative displacement. You see a man-made fan. This is a net that is put by, this is a man-made thing. This is made by Mother Nature, right? Okay. Then these are the time scale of the earthquake. This is the time scale of earthquakes, of a number of earthquakes repeating on the same fault. And these are the scale of the plate tectonics of a large number of earthquakes that have been moving and taking place within the plate boundary. That has one fault system. Very simple system, right? So then if you pretend to work on the earthquake cycle of the San Andreas, you need to do earthquake seismology, and then you need to do fault earthquake tectonics as well, active tectonics. Okay? This is tectonics within a time span of interest to the society. This is exactly the definition of what active tectonics is. We're not asking you to go back to Jurassic time or, very, very old geological time span, but you need to do tectonics within a time span of interest to the society. And the tectonics that is within a time span of interest to the society is depending where you are, if you are within a plate boundary region or within a stable region, is this. And if you do active tectonics 1 million, the last 1 million, then you're doing tectonics of interest to the society. Okay. But if you have to say something about an active fault, you can't do just as geologists would do, give a map of a fault and then stop there. You need to tell us exactly what is the behavior of that fault, how that fault is behaving now. And what is the time span of interest to the society? What is the definition of a time span of interest to the society? It's the time span of the built environment. It's the time span of this building. It's the lifetime span of a building. Because at the end, the seismologist has to give design ground accelerations by which the built environment will withstand the shaking that is induced by a fault. And the time span of interest to the society is the lifetime of buildings, is the lifetime of man-made stuff. So then, Now I'm getting you into a very simple, this is really, the first lecture will be extremely easy and accessible. And now let's start getting into what we call the physics of faults. So a fault is a discontinuity within the system, okay? Take it as a 2D discontinuity, okay? Its physics is exhibiting what we call a stick slip during a quiet period, during the peaceful period of that fault. When the fault is not generating an earthquake, it's stuck and it's locked, and you leave peacefully. But it is loading energy, it is loading strains. Okay, if that fault is in the Himalayas, and if that fault is oriented specifically to account for the strains from the plate boundary, okay, and that fault may look peaceful, but it's loading up, right? And this is what we call a stick slip behavior, or a stuck. It's the fault is stuck, and then the fault slips. Versus what we call the stable sliding. The stable sliding is when a fault is continuously moving, okay, without releasing energy. And let's look at these very simple quantities that you need to bear in mind. We've been arguing that slip will be our favorite parameter during this course module. We'll not be talking about waveforms, but I will always try to connect to what you've learned in seismology. Then an earthquake is caused by a sudden slip on a fault. You know what an MW is, a moment magnitude, okay? M0 is equal to, seismic moment is mu, which is the rigidity, S, which is the surface, U, which is the average slip, right? Then from M0 you have the moment magnitude. So an average slip for a magnitude or moment magnitude of 4 and 5, shallow earthquake within your crust would generate an average slip of few centimeters. Not at the surface, on the fault. In general, a magnitude 4 and 5 has, the fault does not come to the surface in general. Okay, but the slip that you'll get on the fault, okay, the average slip that you would get, that you would use to reconstruct the magnitude, then this is the slip within your centroid. Okay, you should know what the centroid depth is. Should be of the order of few centimeters. In magnitude 7, we're talking about few meters on the fault. In magnitude 9, we're talking about 10 to 20 meters on the fault, which means it could be of the order of 7 to 8 meters at the surface, if the fault gets to the surface. And these are average slips when the fault is behaving, is releasing the energy in a seismic fashion. While when the fault is loading up, we talk about slip rates. Slip rates. A rate is a velocity, but then these are millimeters to centimeters per year. It could be less than a millimeter, okay? And these are slow deforming faults, okay? And you need to have these values on the back of your mind. Then what happens to the slip during your earthquake cycle? We talk about two types of slip. Okay? We're introducing slip. We talk about stick slip, which is the seismic one. Okay? This is the slip that happens after the phase by which the fault is stuck. And this is your co-seismic slip. It's two sides of the interface are stuck together thanks to friction. They are stuck together because friction is keeping them there, because friction is far stronger than the elastic restoring forces. And the two parts of your fault are stuck together, right? And then when the slip occurs, basically, co-seismically, it's when the friction is overcome by the elastic restoring forces within your system. And the slip is controlled here by a dynamic friction. We'll define what dynamic friction is. And it's controlled by heating. Because you will see that friction, it's not a single value parameter. typical seismic phase. You will see that it's a complicated object. Okay? Another type of slip, which is the seismic slip, this is the continuous sliding, or what we call the stable sliding. This is called unstable sliding. Okay, this is called stable sliding. It's the two sides of the fault, they slide continuously past each other with 1 millimeter, 2 millimeters, 3 millimeters, 4 millimeters, or whatsoever per year. So this is one part of the continuous spectrum of deformations that I've been showing to you in the beginning. Okay? Then this is a seismic deformation. In between the two, you have transients. Transients, it's a slip that takes place and then switches off and disappears. Or it's a slip that takes off and then gets started and ends up with a large earthquake. Or it's a slip that takes place after a large earthquake and stops. Then transient is something that is not steady state. It's not happening continuously. Right? And you will see that now the big fun is in chasing transients. Chasing transients both in seismology and space geology. Okay? And we'll be we'll be getting into this in details. So then, this is friction. Okay, this is a wording coming from Leonardo da Vinci. This building is basically, it's the building called Leonardo da Vinci building. And then there will not be friction anymore. And the sound will cease and the dancers would stop. So he's getting you into acoustic waves that you learned with Fabio. And then he's stopping, basically, when you can't, what does it mean? It means that the elastic restoring forces are less than the friction. Okay, then you stop. That's all. But there might be a geometrical issue as well. This is, if you're a bad dancer, and you distribute badly your weight, or you rely on your partner. Okay? And friction is extremely important. Understanding friction is really important. And the first understanding of friction came out from rock mechanics experiments. Okay? And thanks to rock mechanics experiments of friction within the lab, okay, this is what I call rock mechanics experiment, we started learning more about friction. Before we get into a rock mechanics experiment, this is what we call a simple analog of an earthquake. Okay, this is what we call a spring slider, or if you talk to a statistical physicist, he would call this a Birch-Knopf model. Okay, Leon Knopf is a seismologist that was also playing the violin. He's now a standing fellow. He visited ICTP several times, and now he passed away, unfortunately. He's a giant. The spring slider model is exactly the model that allows you to study the mechanics of earthquakes and faults. Okay, so this is a mass, M, that is put over a surface, over the table. And here I put a spring attached to my mass. Okay? So can you tell me now how these analogs compare with real parameters of your earthquakes, with the real kinematics of the earthquake? Then what the mass represents, and what the spring represents, and what the arrow represent. We say that an earthquake is basically an instability on a fault, and this fault is embedded within a medium, and this medium is under strains thanks to plate tectonics, right? And then in my first slide today, I've shown you that we need to understand how straining plate is transferred to faults, right? Then a spring slider model basically exhibits a mass over a surface, and this mass is attached to a spring that I pull. So if I take a mass, by the way, we have a spring slider at ICTP that I developed with my former students. You could look at it. And if I have a mass, and then this mass is attached to a spring, and then I pull the spring, what would happen to the mass?
Suddenly slide down and stops.
What would happen to, if I pull the spring, what would happen to the mass?
There is a friction. As soon as you start to pull it, there is a friction that tends to stop.
Then
the
you
slide.
mean that if I pull the spring, the mass will start moving?
No.
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 Why?
Because in your top, your force should overcome the friction force between the mass.
No, you're getting too fast. No, it's completely wrong. Your answer is wrong. Why the mass does not move? He's saying, no, the mass is not moving because friction is already working and then keeping the mass.
Because of the spring, like we were pulling it and the spring is being deformed. And after
Yes,
pulling, we will have the
absolutely. Then if I pull the spring, I need first to load the spring before I reach the mass, right? Once the spring is loaded, then extend it. Then once the spring loses its, becomes like a straight line, it becomes like, it's connected to the mass, and there I start acting on a mass. But the mass won't move at that point because of the friction. So, then in real Earth, what the spring represents, and what the mass represents, and where is the fault and where is the friction within this model? Yes,
The fault is between the mass and the horizontal surface,
that's perfect.
and the spring shows the movement of the medium,
No, the movement of?
the plates or the faults.
Well, if I start speaking now, I'm giving the answer. So, then the spring should be representing what? We say that an earthquake, it's an instability, it's a frictional instability over a fault, and the fault is embedded within the lithosphere. And the lithosphere is strained by the plate tectonics, right? So, where is the lithosphere in this analog?
The spring.
It's the spring. It's the spring. Your fault is embedded within the lithosphere. Before I deform the fault, I need to load up my lithosphere, right? Then I need to load up my spring before I reach the fault.
Yes.
And then it's only after having, charged my lithosphere, loaded my lithosphere, that I start acting on the fault. And then when I reach the fault will start, friction will start reacting. Right? Okay? So what is the plate tectonics here? What is the engine of all the deformation? And this analog,
The arrow.
the arrow. The arrow, it's my, this is my hand. I'm pulling the spring. So this is plate tectonic. I'm representing the plate tectonics here. So the spring will be the lithosphere. The interface between the mass and the surface will be the... And here, basically, it's very simple. Then we're representing the elastic restoring forces here. If the elastic restoring forces are smaller than the friction, so you see the vectors here with a module, time, this is very simple, right? This is my module. The module here is telling me that friction is stronger. Then the block is held in place. does not move. Okay? And I will start now charging the spring. Then I reach a level by which my elastic restoring forces will come almost similar to the friction. Then moving load point increases the elastic restoring forces. And then the slip occurs when elastic force exceeds friction. Pum, and then you get the kick. Right? And here the friction drops down. Or the elastic restoring forces get higher. Which of which? Yeah, there are several people that got a PhD. There are maybe food professors in seismology that do not know this. But still, I mean, if you think about it, you will see that there is an issue. Physics is fantastic. So here, a slip, you're not supposed to give me an answer now. It's better. Then at some point, the block has to stop. Then the elastic restoring forces or the frictional forces will become bigger than the elastic restoring forces. This is why the block stops. If the frictional forces are not higher than the elastic restoring forces, then the block won't stop. Okay? And you see that friction is behaving in quite a funny way. Okay? And it's friction that controls the whole picture here. Okay? Then this is the frictional instability, and then we're getting into very complicated things, but we will be looking at these things later on. Okay? And I'm getting into dynamic versus static friction, but before I get into this, I would like to explain different things, okay? So I think I will stop here because we have a faculty meeting for now. Let me just switch this off.